odd numbers, odd point releases are going to be cleanup releases. We've got plenty of cleanup to do in Mahout. And then the even ones are going to be extension releases where we'll have new functionality. 0.7 was our first cleanup release. I think I deleted personally something like 100,000 lines of code. And it's not easy too. And we also merged together several libraries, made it because nobody was consuming the separate libraries separately. And so I'm going to talk about that, and I'm going to focus in on particularly some new developments that a customer of ours worked with us on. They sent 6 developers out to Silicon Valley and spent 2 weeks, and we knocked together some exciting nearest neighbor and clustering technology. For the most part, and as far as I know entirely, this is not a MapR talk, it's an Apache talk, so Red Hat goes over there. But even as my hat comes off, we have a whole bunch of hats up here, and Macy has very cleverly arranged that each of the little folders that you have, that you were given as you walked in, has a number in it. Later we will bring up some random number generators, and we will select people. You will get a hat. Of course, it will not be the black belt edition. This is, of course, the black belt edition. Y'all will get the white belt edition, but I'm sure you can upgrade it. So let's get into it here. So pretty much what I'm going to talk about is what happened in 0.7, and then move into the new stuff that I'm working on with this customer in the other thing. And of course, the basic big step in 0.7 is there was a lot of dead code that had been contributed, or it was a student project and never really got up to the quality that anybody really wanted to use, or somebody had an itch and said this would be so cool, and they were wrong. That happens a lot. It was an exploratory phase. We wanted to expand in any direction anybody wanted to go, and then we wanted to let it sit for a bit and steep, and if it didn't look useful, we'd cut it out later. That was that. And the basic technique for cutting the code out that we used was this. Delete it. So for instance, the genetic algorithm stuff, it's just gone. Like that. Blank slate. There were other things that were a little bit more subtle to get rid of. We took, for instance, originally the Colt numerical library from CERN, adapted it, improved it, sped it up, make it more extensible and less generic at the same time. And so we also cut out a bunch of the stuff in that. We marked all of it deprecated once upon a time. Then as we used it, we would add tests. Colt sadly had 0 tests. It was just, kind of optimistic code. And so we would add tests to it and mark it as undeprecated as we used it. So part of 0.7 was to go through a lot of that stuff and say, it's deprecated still, nobody cares, or it's deprecated still, I'm sure somebody cares, they just don't know. So I'll test it and bring it up to snuff. And so we've jettisoned a lot of that crufty old stuff. And so there's probably big holes in our math library now. But there was a lot of abandoned code, and the abandoned code typically was low quality because it was generally written by fairly naive users that were being brought in as an inclusive policy, and they never kind of got any further. And if there were no users and no maintainers, that's a pretty good hint that nobody cares, nobody wants it enough to really do that. And if nobody else cares, why do we care, was our logic. And our conclusion is we don't. It's gone. This is, of course, past tense. So the old latent lay allocation code, which is 20 times slower than the current stuff. The only place that ever picked it up was Apple. They sucked it in, they completely rewrote it anyway and made it the basis of genius. But it's gone now. The old naive Bayes was cranky and weird. It's gone. Genetic algorithms, nobody cares, they're not scalable. Conflicts with mission, nobody cares, they're gone. If you do care, you should get on the mailing list. Oops, too late, it's already out. But you could find it, you could resurrect it if you wanted to. But that's the basic policy. If we spread the word, sent the original authors an email, and nobody cared to come back, it went away. We also took, our original design is we had some fast primitive collections. And we re-implemented that, sadly, because all of the comparably fast collections algorithms that did primitive collections, notably Trove, were GPL. And we couldn't get a clear statement on licensing, and so we said, fine, whatever, we'll just re-implement those. And we kept that as a separate library because that seemed like a really useful thing in and of itself, not just as a part of something else. And it appears we were wrong. So we sucked that back in for the math library. There is no independent Mahout collections library anymore. You still can get the 1.0 distribution, you will be able to do forever, but otherwise it's gone and sucked into the math. And collections is the heart of the sparse math code in Mahout, so it makes a lot of sense that it really is just in that same library, right next to it anyway. You can imagine a sparse map of integers to doubles. It's a pretty short walk from there to a sparse vector, for instance. Things like that. And so nobody really cared about collections as it is. We needed it, so we sucked it into math. In doing so, I broke the build. Sadly, there were code expanders that were fighting over things. But that's the nice thing about open source is somebody else fixed it for me. I got to break it, they got to fix it. It's a nice division of work, at least as far as I'm concerned. We also have been experimenting with integration of Mahout into higher level languages. Mahout's kind of a pain in the ass to use. Yeah.
You just say a couple of words about what Mahout is? I mean, I know that it's a
wow, cool. Good idea. So Mahout is an Apache project. It's a couple of years old now. I guess 4 or 5 years old. It's I thought it was a very young project. I may be wrong. Eventually, I will be wrong. And its goal, its remit, is scalable machine learning. And I was talking to this guy over here earlier about what that means. So he said, well, do you mean kind of like numerical recipes? And that was a great question because there is a strong opposition there. Numerical recipes, for all of its faults in implementation or copyright or whatever, was an interesting snapshot of what was interesting generally in numerical analysis, practical and numerical analysis in the early 90s. And it had a lot of dense algorithms, dense matrix algorithms in it. And those turn out to be relatively rare in scalable applications. And if you think about it, the cost of a matrix-matrix multiply is n cubed. So even if you keep the width constant, it's going to be squared in the number of rows that you have. And that is, in itself, the definition of unscalable. Scalable means that you have a unit of input, and with a constant amount of time and a constant amount of memory, you can handle that input. Because anything else gets out of hand. And maybe it's sublinear, and meaning the cost decreases, or something, but memory and time load per unit of input has to be constant. So in general, the resources required are linear in the size of the data. The resources could be time, something we all got, but it cost us, or it could be computers. Not all of us got it, but we can buy them if it's worth it to us. But it has to be linear in that scale. So there's a lot of things that are just right off the bat, out of bounds. Our remit is not to be broad, it's to be scalable. So if there's some new whiz-bang thing, and it's obviously not scalable, it's not us. If there's something that's well demonstrated, has traction, has demand, and it is scalable, hey, then it's interesting. But so part and parcel of that is the sparse problems. Many of these problems that invoke scalable, the need for scalable solutions are sparse. So imagine a classic problem. You have words attached to a website, a page, an ad, a description of it. You have word-like things like a user ID. And you have other word-like things like an ad ID. And you have the interactions of these. Well, you have a feature space with billions and billions, to quote Carl Sagan, the only man who could ever talk in italics, billions and billions of features. And you only have a few thousand of them that are non-zero in any given data example. It's really sparse. And these are classic kinds of problems. Because even if the notional width of the matrix increases, like it does as you look at language, the number of words you've seen increases without bound, the number that appear in any given document does not. So you get scalable algorithms. So that's what Mahout is, scalable machine learning. And frankly, up to now, it's been kind of cranky, hard to use scalable machine learning. So one of the key problems is how do you make it easier to use? One way is to support it from high-level languages that are already very scalable, like Pig.
What are the current APIs? Java is the current API?
Java, period. And kind of consistent APIs. And where Mahout works well and is commercially used at dozens of companies is recommendation systems. And where it works pretty well and is used at several companies are the classifiers. And where it works not so well and it's used by everybody who wants to try it is clustering. And then there's a few things off to the side, or stuff as I describe it, including very large scale singular value decomposition, which is some of the largest and fastest SVD's code that I know of, where it can, in a few hours or less, do the SVD of the entire Twitter social graph, for instance. The stuff category has some very interesting stuff. 0.7 is, I think it was at 0.6. Definitely at 0.7 and 0.8. That's in use by Twitter, in use by LinkedIn, and used by other people. There's 3 or 4 versions of it to do different things. But none of that's accessible from things like Pig, and that's a real problem. And so I sat down and started trying to work on ways to do this. And one of the things that people have real fits with is the idea of how you vectorize these features. You have to have vectors that go, numerical vectors, you know, in dimensional, n by 1 matrices, and or 1 by n, whichever way you want to think of it. But you get these features in the real world that have billions of possible values, and having a vector that's 100 billion long is just not going to happen. For one thing, it's really convenient to have integers be the index of the vectors. It's just a little bit of a sanity check for one thing. And so text vectorization, or text-like vectorization, or user ID vectorization, how you smash this 100 billion or quadrillion number of features into a vector that's 1 million long, escapes a lot of people because it's an obscure thing. And the way that we do that usually in Mahout is with a randomized projection. It's like a Bloom filter. You pick 2 or 3 random locations based on a hash, places in that vector where that element will live. And it will get stomped on by other things, but as long as they don't stomp exactly synchronously, you're cool, because you can reverse engineer the original space. You've just done a dimension lowering random projection, which is well outside the bounds of the Johnson-Lennonstrauss theorem, so you have a good projection. But that's hard to say in email or on one paragraph of text. And so Pig vectors, one of its primary goals is to support that vectorization well, and to support some of the simpler classification APIs that we have, and to allow model saving. So these are the first features that were implemented. And at this point, it kind of works, except for the fact that nobody else but me can build it, and aside from the fact that the syntax is a little obscure still. But that's progress, and I think that there's some real interest on that. Twitter has an implementation that matches Pig vector in a lot of interesting ways, and they did some cool stuff, like they made it work for real, and Pig vector has some interesting stuff like very nice R-style expressions that describe the dependencies in the classifiers. So it's kind of easy, kind of hard. It's all Maven based, but the first version of Pig vector depended on elephant bird which in its early versions depended on unreleased software somewhere else, and the author wouldn't mavenize it, and it was just a mess. More recently, there's a newer version of Elephant Bird that is buildable and usable. So here's a little bit how it works. So tokenization is done using a text encoder. Ooh, and there's a little laser here. It doesn't work. So I'm going to use the old style pointer. This in code vector code here says we're going to define a function called encode vector, and it's this class encode vector. It's clever naming, and it's going to produce 10-dimensional output. The output is going to have the x and the y variables and an offset variable in it, in the 10-dimensional output. And the schema of the input given to it is x is numeric, y is a word-like thing, and z is text. Text is a sequence of words. And since z isn't even mentioned here, it will be ignored, but it will be accepted. So the idea is that you can express how you do the encoding in a nice symbolic form. This is stolen from R. The R has a very nice expression syntax for doing exactly this kind of thing. You can also put here on the text, you could put parentheses, and you could mention a Lucene analyzer. So you could say text Chinese. That'd be kind of cool. So you'd be able to say what kind of text it is. Or text webbish stuff, where you would remove boilerplate text and find URLs as singularities and things like that. The formula there is not normal arithmetic. It describes the parametric structure that you want to encode there. Plus means also use this variable. And you can put parentheses around groups and then a power on that. So you might say x plus y plus z. It means use those three variables, parentheses, squared. And that would mean use x, y, and z and all their two-way interactions, or cubed. And it would also include x, y, and z as an interaction, which gets pretty amazing when x and y have text and z has a word in it. You know, you can have pretty amazing large feature spaces this way. The only limitation, of course, is that that syntax doesn't actually do anything right now. But it's really cool syntax. And it's sitting there waiting. And we have the encoders to do it. It's just not plugged in. Other than that, it's very nice. So here's how you would do it. You would load data, as in that first statement there. Standard sort of load. We would use pig storage for whatever encoding you want. And we declare the schema there for convenience. Now we encode it. And if you remember, we defined the schema for the encoder separately back there. So we have a little bit of repetition here, which is unpleasant. And star here is all of the records in the set A. And pig has a very subtle syntax and semantics there, sadly. And so that's a point of contention there, but that's not so nice. And then we store this out using a sequence file storage and have some magic incantation here, which says this is the class that will write the key. This is the class that would write the vector. Those are the second and third to end last lines in this line. And then the last line is what is the type of the generic that is being written out as the value. Now, I find this syntax, in spite of parental pride and all that, hideous. And so we really need to improve it somehow. All this does at this point is say this sort of thing could be done. It really doesn't say that it should be done yet. And you really begin to see that here where we define the train function as a logistic regression with this massive and bizarre set of arguments. It says we're going to do 5 iterations. We're going to do it in memory, so it'll run as a reducer, a single reducer. We're going to use 100,000 features, which has to match the encoder. Yet another dry violation. And here's the categories that are going to be output. And this is another string with magic syntax in it. It's congenial syntax inside it, but not such a good thing that there is special syntax there. So it isn't done. It is ugly. Doesn't quite work, but it does seem to have some real promise in there. Because even with these warts, I couldn't have explained how you actually use the classifier libraries in Mahout in that few slides. and with that little amount of hand waving. There's actually explaining the Java interfaces is harder than this. So I think there's some real promise here. And the guys at Twitter are finding rapid adoption of PigML, which is very similar. So I think that's another indicator of promise. This probably is not a 0.8 thing. It might be a 0.10 thing. Or it might be a 0.8 thing if there's somebody out there who is all excited about this and wants to work with me on it. We ought to be adding more models. We ought to simplify the syntax. We ought to use a new version of Elephant Bird, or maybe we ought to throw away and use PigML. But there's a real roadmap of things that need to be done there. Now, that's what 0.7 really involved, or what it could involve. And from here, I want to talk about a project which is on GitHub right now under my account /KNN. It's slated for adoption into Mahout. I want to make real sure that all the IP is clear. All the participants have said it is, but I want to make sure of that. That's an important thing to do. And I want it to be a little bit more mature and fit into the Mahout APIs for clustering before it actually goes in. But if anybody wants to use it right now, certainly can. And it has some interesting and aggressive properties. So the goals of this project were to cluster very large data sets in order to facilitate nearest neighbor modeling. We wanted to allow a very large number of clusterings so that we could do high dimensional nearest neighbor sort of problems. So for instance, k-means clustering typically has cost proportional to the number of clusters that you use, and proportional to at least the number of data samples you have times at least log of the number of data samples, because it doesn't converge real quickly. So you have to pass through the data many times, and every step of that is linear in the number of clusters, because you have to find the nearest cluster. So we wanted to improve that scaling dramatically, and we did. We also wanted to get good quality in the sense that the clustering would generalize well, that the average distance to the nearest cluster on unseen data would be small, that it's a good quantization of the input distribution. This isn't quite what most people think of when they say clustering. It's what the telecommunication industry might call vector quantization or something like that. But that's the goal here. Because it's going to be used as a part of a nearest neighbor thing, we don't really care if it represents real clusters or things like that. We just care that the generalization distance, the entropy and the generalization to new data is good. It's all based on the Mahout map package. It runs on Hadoop, so that's a goal anyway. It turns out that it doesn't need to run on Hadoop in order to be fast. And the goal is to be fast, which is to run way faster than anything else we have. Non-goals, things that we didn't care about. No one cares. We didn't care if we used MapReduce or not. If it could be achieved on a single machine, or if it had to use a different programming model, fine. Not a thing. We didn't care to minimize the number of clusters. Just not a goal. Wouldn't hurt, but not a goal. And we explicitly did not care about supporting any metrics other than square distance. There's a huge economy available in that assumption, but there's also huge assumptions that come out of that. L2 is not an appropriate metric for a lot of problems, even though you can kind of shoehorn it in a lot of times. But for another day, we'll deal with that another time.